All right, g'day everyone. Welcome to Aries Workshop number 2 for Sem 2 2021. Today we're going to be discussing how to perform computational fluid dynamics, or CFD, using the Ansys software package. And we're going to be performing fluid dynamics around the body of a rocket and making various calculations to see crucial values to make sure our rocket doesn't spiral out of the sky. But CFD is really valuable for all sorts of different engineering problems, not just rocketry. So this is a really powerful tool that you'll be learning today. And let's just jump straight into it. So we're going to be using the Ansys software package today to perform CFD. It's really the world leader in engineering simulation software. It's the largest in the world, and they only do this software. That's all they do as a company. So they have a huge range of software available, and it's really powerful. I'd just like to give a shout out to Leap Australia. They were really helpful in helping me pick up a lot of the knowledge that I'm about to share today. And I will show you that they have some tutorials available as well. And they're a partner with Aries, so they've been really helpful for us in learning this Ansys software, and they also provide tutorials for other software. So what is Ansys? Ansys is a group of different software that allows you to perform various engineering simulations. This includes tools for just basic 3D modeling, CAD, and it also includes fluid dynamics and structural mechanics, FEA, so stress strain analysis. You can perform thermal simulations, electromagnetic simulations. There's a huge range of simulations that you can perform using their group of software. And you can also combine them into multi-physics simulations. So for example, you can analyze the stress strain of your model and then couple that with the fluid dynamics simulation to see how the fluids flow around the deformed body, and you can couple them together to get really realistic stuff. So thermal and fluid dynamics, you might want to mix hot and cold water. You could have the fluids and the thermal coupled together to get a lot of information of various different simulations. Today we're going to focus on CFD, of course. So why CFD though? Why would you want to learn this tool? Well, it allows you to numerically solve fluid space problems, and it's very expensive to perform experiments with if you're designing something that involves fluids problems. And especially if you're iterating your design, it's very difficult to find the resources to perform repeated experiments with different iterations of your design. So having a numerical method to do this saves you a lot of time and money. And you can solve for various information about your system, like the pressure distribution, the velocity of the airflow around your body, the temperature distributions. And a big thing in aerospace is you can use that to approximate the lift and drag forces and find the location of the center of pressure, for example. And that's obviously really key information for an aerospace engineer. So this is a really wonderful skill to have as an engineer, particularly in the aerospace industry. So how do we use it exactly at Aries? So we take the open rocket data and we want to model that into a 3D rocket model. And then we apply our CFD analysis on that 3D rocket model and compare that to the open rocket data. And we're in this constant iterative loop of, okay, how does the 3D model match with the open rocket data? And we can actually feed in our really accurate CFD information into OpenRocket and then simulate our flights using that updated accurate information. So we might take the C, P, and CD, which is a center of pressure and drag, put them into OpenRocket, and that'll allow us to get more accurate simulations out of OpenRocket. And I'm going to explain, for those of you who aren't familiar with the software, here's the full hierarchy of software that you'd need to do this workshop from start to finish. In semester 1, we provided a series of workshops on anything that you would need up to this point today. So we talked about how to create rocket models in OpenRocket. That's a 2D model software. And once you are satisfied with your 2D rocket model in Onshape, you can then watch the workshop on how to convert that into a 3D model in Onshape, which is 3D modeling software. And then you can take that 3D model, bring it into Ansys SpaceClaim, which is Ansys 3D modeling and meshing software that we'll get to. And you can prepare your geometry for the CFD. Then you finally put it into this program called Ansys Fluent, which is the actual CFD software where you perform the solution for the fluid around the body. So we're going to be using SpaceClaim and Fluent today, just in case you're wondering what those words mean. There you go. So let's just go again over the design workflow. So we're all on the same page. We take our 2D model in OpenRocket and we convert that into a full 3D model in Onshape. And then we clean up this Onshape model and we make a simplified version because it's easier to perform CFD with a simplified model. And then we export that as a .sat file, which we'll get to. And we put that into SpaceClaim, make some further geometry modifications, including slicing it into quarters in this case, because it's a symmetrical rocket. And then we'll take that SpaceClaim document, put that into Fluent, which is the actual CFD software, build a mesh around the rocket, and finally solve for the flow. So there's quite a few steps, but we're going to take you through these steps one by one. Before I get into the details of that, just for those of you who want to join with me, here's everything you're going to need to get set up for this workshop. There's the Aries GitHub, links here. And this has the list of all the previous workshops, all the previous tutorials, including the videos for how to use OpenRocket, how to use Onshape, and how to convert that into a 3D model. So I would recommend that. To download OpenRocket, you can just go to openrocket.info, press that download button, and it's really, really easy to install OpenRocket. It's pretty self-explanatory. For Onshape, for those of you who don't have a license, you can request a trial license and choose your country and just go to student license and you can request a student trial license. Otherwise, you can contact one of the Aries committee members in the Slack. Probably Harrison would be the first person to go to if you wanted to get an ongoing license for Onshape with us. So I'm going to show you what that's like now. So once you have an account in Onshape, you can sign up and you'll have a list of models to work on. And this is the model that we're going to be working with today. And once you've got Onshape open and good to go, you'll want to download Ansys for students. So if you just Google Ansys Student, it should come up as the first result. Just scroll down to Ansys Student, download now, and click that big yellow button there. It'll have a 12-month license, and it's going to be slightly limited functionality, but for everything we want to perform today, it will be completely fine. So install that, and that should look like this in your, you'll have a whole list of programs when you're ready. And if you've done all that, then you're good to go. and follow through with this workshop. And let's go back to the slides. All right, so the first thing we need to talk about with CFD is you have to prepare your geometry to make it modelable in CFD. There are a lot of little manufacturing details and CAD details that are not important for CFD, and CFD can't handle complex geometry. As you'll find out, the more complex your geometry is, the more complex your mesh is, and that takes a massive toll on your computer, and it doesn't really affect the end result. So you can see I've got some bolt holes around near the nose cone of this rocket, and I've also got this external geometry, these sort of vents. For CFD purposes, they're not going to change the results that much, and they're just going to make it much more complicated. So what you need to do is remove that kind of stuff. And we're going to build our simplified model in Onshape first. You can do it in Ansys, but I recommend strongly just doing it in Onshape. And then you can directly import your simplified model to Ansys. The reason I say that is Onshape is a lot easier to use, and Ansys isn't the best 3D modeling software out there. So I would recommend just start with Onshape, take your full model, such as this one, and convert it into a simplified model. And this is just a full solid block. Okay, you can see that this model has a hole here where the motor is, and it's all hollow on the inside. Okay, even up into the nose cone, it's hollow. This one is just a solid block, and I've smoothed out this surface, and I'll get into how to do that. But the point is, you need a simplified model for CFD. So we've got small faces and manufacturing features, just remove them in Onshape. Fillets, chamfers, rounds, remove those as well. Just make it a smooth surface, because those are going to make it a lot easier to perform CFD. Are there any irrelevant features that wouldn't influence the flow that much, such as those dark gray features that I've got on the outside of the rocket? Just remove them. It's not going to affect your results. So once you have your simplified model and you're happy with it, go to Onshape and you can export it. You need to export a single part that has the entire rocket and export it in the Ansys format. That's just a particular file format that translates well to Ansys. If you use other file formats, it's fine, but there might be some errors associated with switching file formats around, and Ansys is only compatible with certain file formats. So I'd recommend using this Ansys format. It will minimize the risk of any errors when you import it to Ansys later on. Okay. And you'll get this .sat file once you've exported it from Onshape. So I'll just show you what that looks like. I select my simplified model, go to export. The export window comes up, format Ansys, download it, and it'll come up over here at some point. Okay, and what you want to do is want to open that in SpaceClaim. So we're going to go to our Ansys software, scroll all the way down to SpaceClaim, which you'll remember is the 3D modeling software in Ansys. And we're going to use SpaceClaim to simplify our 3D model a little bit more, and then we'll put it into Fluent, which is the actual CFD software. So just wait for that to open. You can see there, I've got my SAT file. It's just in my downloads folder at the moment. Okay, so this is SpaceClaim. And what we're going to do is file, open that SAT document. You'll have to go down here and you'll have to go all supported files. And bingo, there we go. So we have our rocket open in SpaceClaim now. All right, so now that we have it open in SpaceClaim, If you want to mess around with the mouse controls and make it similar to Onshape's mouse controls in terms of rotating the model around, panning, all that kind of stuff, you go File, SpaceClaim, Options, Navigation, and then you can change to what you want. I put it so that it's similar to Onshape, so that my mouse controls are the same across all my different software, because it's really annoying to go from one software to the other and they all have different mouse controls. So I would recommend doing this. What we're going to do is we're going to put the origin in SpaceClaim right on the tip of the nose of the rocket. And we're going to point gravity, which is the Z vector. We're going to point that down the rocket. Okay, so we want the tip of the rocket to be right on the origin. So what we do is we triple click on the rocket and we're going to have this move tool in the sketch tab. So let's go to the sketch tab, move, just triple click. And then you're going to take this triad, this object here, drag it right onto the tip of the nose cone. It should automatically lock on there. Then you're going to drag that green arrow 180 degrees. And you're going to click on this button on the screen, which means move up to. And you're going to move up to the origin. So I'll show you what that means. Each tool in SpaceClaim has various options in the top left corner here. And one of those is the up to tool. So firstly, let's rotate around 180 degrees. And then drag this blue arrow, hit up to, and then just click on the origin. And bingo, we're good to go. Press escape, and now you can see, whoop, just do that again, up to the origin. Beautiful. All right, so you can see that our Z axis is now pointing straight down the rocket. This will just make it easier later on when we have to measure things. And I'm just going to change my mouse options really quickly. I want spin to be the right mouse button and pan to be the middle mouse button. So that's going to make it really easy to measure things in Fluent because we'll have the origin right on the tip. Otherwise, you won't really know where you're measuring from. I made the mistake of having the origin somewhere out in space, and then I couldn't figure out in Fluent where the origin actually was, and I was getting really weird measurements. So I would strongly recommend putting your origin somewhere really easy to understand before you put it into Fluent. Okay, so why SpaceClaim? Seems like an extra step for no reason. The reason we want to put it into SpaceClaim is you can't directly export your ASYS file from Onshape into Fluent. You have to convert it to this file called a SpaceClaim document, and that's what Fluent understands when it imports it. And SpaceClaim has a few extra features for simplifying your model and double checking that everything is good to go before you put it into Fluent. So it can check for things like missing faces, split edges, which is just this curved edge might be broken into about 8 different pieces and it just combines them into one. Extra edges, small faces. You can see there's a really tiny sliver face there. And all of these kinds of things are going to make your CFD slower and more difficult, and they're going to make your results harder to interpret, and it's just going to be worse. So it's best to further simplify your model, get rid of any rounds or fillets, get rid of any short edges to simplify your CFD and just make it quicker and less likely to throw an error. Now, at the top here, I've shown the location of all of these tools. They're mostly in the Repair tab and the Prepare tab. And I recommend just going left to right, just going, okay, do I have any missing faces? Do I have any split edges, extra edges, etc.? Move along and then go across to the Prepare tab, go left to right. So let's do that now. We're probably going to be fine here. but let's just click missing faces, and it says at the bottom, no areas found. So because this is a really simplified model of a rocket, we're probably not going to have any errors. But if you did have a missing face, you'd tick that tick and it would fix all the missing faces. For example, if there was a tiny face missing somewhere here, it would fill that in. And you need everything to be airtight for CFD. You can't have any missing faces or holes in your model. Extra edges, no areas found. Duplicates, no areas found. Okay. Small faces, all good. And we can go to the prepare tab. We can check that there aren't any rounds. Well, we actually already removed all of the fillets from Onshape, and any small faces or short edges, it's not coming up with anything here. So we don't actually have to prepare anything here. If you were going to, as I said, you just click that tick and it would automatically fix everything. But because we did the initial simplification in Onshape, we don't have to worry too much about this step, which makes your life easier. All right. So another thing that we can do is double check that our problem is symmetric, and this will save you a lot of time. So the question you need to ask yourself is my model symmetric? And is the flow around that model also symmetric? So if the air is flowing directly down that rocket, then we can say the flow is symmetric and we can split it into 4, okay? However, if the wind was blowing at a 45-degree angle onto the rocket and it wasn't symmetrical anymore, we wouldn't be able to split the flow into 4, okay? Despite the rocket itself being symmetrical, if the flow is not symmetrical, you can't split it, okay? So let's split this rocket into 4 because we're going to assume that the flow is going straight down the body of the rocket. We're going to go to the design tab and we're going to make a couple of planes. Going to select the y-axis and the x-axis, and they're going to create planes normal to those axes. And because our origin is right on the rocket, it's going to be really easy. We don't have to move the planes anywhere. So let's go to the design tool, design tab, plane, click there, perfect. All right. And then you'll notice in the structure tab here, this lists all of your bodies and features that you have in your model. We'll get to this later. You'll want to look at this, but you can see we've got 2 planes. And if you wanted to hide those, for example, you can just tick those boxes and it hides them. But we're going to use the split body tool, which is in the design tab, and that's going to allow us to split this into 4. All right. So we're going to select the split body tool. Then we're going to select the plane and then select the bit of the body that we want to get rid of. Okay. So let's do that. We'll go to the split body tool. I'm going to select the target object. The instructions are always listed at the top left anyway. All right, and then select a plane to use as a cutter. Let's go for this plane here. And then when it highlights in red, that means you're going to remove that part of the model. So let's remove the part of the model that's outside the 3 axes here. Then we're going to select this plane as a cutter. And again, we're going to remove that red bit. And now we've kept the part of our rocket that is inside those axes. Okay, just remembering that the reason we're doing that is it makes it easy to measure distances because we know that the x-axis is pointing towards our rocket. If you had it on the other side, then you might need to look at negative x values and that could get confusing. All right, just press escape to leave that tool. You can actually select these planes and just press delete, get rid of those. We don't need those anymore. And that is getting closer to being ready for CFD now. Now, we're going to create an enclosure around the body. And I think I should explain something. The way CFD works, it doesn't model the actual rocket. What it models is the air around the rocket. So what we want to do is we want to create a volume of air that is like a big rectangle minus that rocket, okay? And if you're not sure what I mean by that, I'll get to it. I've got a question. It says, is there a difference between splitting with 2 half fins versus splitting with 1 fin? Sorry, can you please elaborate on that a bit? I'm not quite sure what you mean.
Yes. So if, for example, you were to split the rocket, so instead of having that sort of quarter, if you rotated that 45 degrees, so you had like the body on either side of one of the fins and then one of the fins down the center of the plane, if that makes sort of
I see what you're saying.
sense.
Yeah, you could definitely do that.
So would that, and would there be any difference in the results that I get, like with the airflow over the fins or anything? Or is that something I'll have to
The symmetry boundary condition would be at a different point because we've specified that the flow should be symmetric sort of around these 2 fins. So it would allow you to get some asymmetric flow around your fin, but it wouldn't affect the results significantly if you did everything the same. And it would probably make your enclosure a little bit simpler because you just have the 1 fin. So that's an option. It's definitely an option, and it wouldn't change the results too much.
I'll have to try it. Thanks.
Okay, so what we're going to do is make an enclosure. We're going to be modeling the flow through that enclosure, which is the air around the rocket, not the actual rocket itself. If that doesn't make sense, don't worry, I'll show you what that looks like. So we go to our enclosure, which is in the Prepare tab. We just press Enclosure, and for every tool, let's just go to the Enclosure tool. There's this Options area near the sort of middle left. And what we want to do is scroll down to Symmetric Dimensions, which is the option for this Enclosure tool. We want to remove that because we're going to have an asymmetric enclosure around the rocket. If that doesn't make sense, don't worry, it will soon. Okay, so we want to create an enclosure that is basically a rectangle with the rocket sitting on that bottom corner or on that bottom edge. And what it needs to be is large enough to fully model the flow without being so big that it slows down your simulation. So the general rule of thumb is take the length of your model. You want that length in front of the rocket, and you want 3 times that length behind the rocket, okay? And you want that length to the side and above the rocket as well. So use that little diagram there as your rule of thumb. Okay. And here's what I mean by the enclosure not including the rocket. It sort of has this hollowed out bit where the rocket was. It's like only the air around the rocket minus the actual rocket. That's what I meant by what I said before. Okay, so what we're going to do is we're going to select this rocket and we're going to adjust all of these dimensions and we're going to set it up like we had. So 370 is the length of my rocket. So I'll just say 370 times 3. And you can type maths and that will be triple the length of the rocket. And I'll do this one, 370. All right. And what else? This one below the rocket, we just want that at 0. You can also press tab to cycle through the different measurements. And that one's already 370. This one in front, we want that to be 370 as well. And this one, we want it to be 370. Okay, so we'll just quickly compare that to our original diagram. We've got the length in front, 3 times the length behind, and length in width and height. So we're all good to go there. We can just press the tick. Now, if I go to my structure and I untick the enclosure, you can see it disappears. If I untick the rocket disappears and we're left with a sort of hole where the rocket used to be. And that's what we're going to be modeling in CFD. Okay, another thing we need to do, speaking of what I was just saying about only modeling the air, we don't want to model the CFD for the actual solid object. So we're going to do this thing called suppressing it for physics. And you want to suppress for physics any solids in your model. And what that means is when you pass it to Fluent, it won't try and model the airflow through that solid. It just won't look at it. It will treat it like a solid. Whereas the enclosure is a pool of fluid, of air. We want to model physics within that enclosure. So we're going to right-click the rocket and suppress it for physics. And what it does is it won't pass that to Fluent. It won't pass the actual solid rocket itself to Fluent. All right, if you wanted to hide some faces that you, say I wanted to select something here, but there were annoying faces getting in the way, I can just escape from this tool and right click on this face, go face, hide face. That might be useful later on. All right. Now we can select individual surfaces of the rocket. All right, we're going to introduce another CFD concept now called body of influence. So essentially what it is it's a 3D region around your model where you want to create a finer mesh. And the reason you'd want to do that is you want more detail about the flow closer to the model, okay? So in this enclosure, towards the back of the enclosure, we don't need like too much detail about what's happening way at the back here. But if we're right on the nose cone, we want really good information about that, okay? So we're going to create a body of influence, which allows you to have finer mesh around that rocket, okay? And that includes the wake region. You need to have a finer mesh for your wake region because there's going to be a lot of turbulent features and vortices happening there. And you also want to create extra bodies of influence around complex geometry. And we'll get to that. So for example, around the fins and the nose, we have really complex geometry, curved surfaces, small surfaces. We need an even finer mesh around those parts, okay? So we're going to create multiple bodies of influence. Let's take a sip. Excuse me. So the first one we're going to create is the far body of influence. All you do is you right click and you just say make a new component. And then you sketch a rectangle on one of the faces and extrude that into a box. All right. So let's go to our model. New component, call it BOI far. All right. And then I'm going to rotate around. I'm going to select this face. And we're going to create a sketch on that face. I'm not the best at rotating the camera for these things. Forgive me. It doesn't have to be perfectly aligned because we're literally just drawing a rectangle anyway. But we might want to draw from, say, there to maybe there. Doesn't have to be exact measurements, but we want to include that wake region and we want to include the region sort of around. Just finish that sketch. And then you can see we have the extrude tool now in the design tab, or the pull tool. And we can just pull that. Again, you don't have to worry too much about exact measurements, but it's, you know, it's a region around that rocket. If you want to change the size of that, just drag it in a bit. Maybe you want to go a little bit further from the nose. Yep, I'm pretty happy with that. Just press escape. And that's our component now. And that's our near body of influence. So we've got a cube around the rocket. And we're just going to triple click on that body. So triple clicking selects an entire body. and right click on it and go to transparent. So now we can still see the rocket. Beautiful. That's our body of influence now. All right. We're going to create another body of influence. We're going to call it BOI near. And this is going to be for the complex geometry, the nose and the fins. And what you'll notice here is that there's two boxes for a single component. So you don't just have to have a separate body of influence for the nose and the fins. You can actually create multiple boxes for one component. So we'll just repeat the same process as before. New component, BOI near. And this is going to be an even finer mesh than we had before. All right, I'll rotate. Oh, it's a bit disorienting. My apologies. Let's sketch on this face. Let's go to sketch, rectangle. Select the face. Go around the nose cone. Whoa. Not quite happy, just press Ctrl Z. All right, I'm pretty happy with that. Sketch around the fins. End the sketch. And again, just extrude it using the pull tool, which is already activated. Just click and drag. Have a look, is it vaguely symmetrical? Yep, beautiful. Click and drag. Have a look again. That's pretty symmetrical. I'm quite happy with that. Press escape. Again, you can make this transparent. Done. Awesome. And that's our near body of influence. So we're going to be able to create an even finer mesh around the complex geometry. Now we're going to introduce another concept called name selections. And this might sound really excessive at first. And you might think, well, I don't really need to do that because it's a simple model. You have to do this if you want to create adequate boundary conditions and meshing conditions later on. So what I want you to do is, I want you to create a named selection in SpaceClaim for any part that you might want to create special meshing conditions for, such as areas where you want to fine mesh, areas where you have curved parts, or areas where you have small faces. And I also want you to create a name selection for any component that you might want to set boundary conditions on. That would be walls, that would be solid surfaces where the boundary condition might be no slip condition where there's just zero velocity, symmetry planes, inlets and outlets, okay? And what you'll actually find from those list of things is that that covers everything in your model. Everything in your model will fall under that somehow, okay? So you have to include every face in your model once and only once when you're creating your name selections. And that becomes crucial later on when we say, okay, I want to set a boundary condition on this surface. I go to the name selection for that surface. It doesn't make sense yet. It will make sense soon. Just trust me for now. You need to create a name selection for each face. So let's start with the bodies of influence. We're just going to triple click that body of influence. We're going to go to this groups tab and click create NS, which is create a named selection. Okay. And then you can rename it to BOI far. So let's do that now. Triple clicking, going to the groups tab on the middle left, create NS, BOI far. So that's going to allow us to select the body of influence later on in Fluent and apply a finer mesh to just that selection. And then we're going to do it for, okay, let's do it for the other body of influence. We can just hide all the other components, Control A, selects everything, create a name selection, BOI near. Okay, that's the bodies of influence done. Now let's do the curved surfaces. This is another really important thing. You'll find that it doesn't mesh curved surfaces very well, so you have to apply specific extra instructions to the mesher for curved surfaces to say, hey, I want you to actually model this curve instead of just turning it into a 45-degree angle. I want it to be nice and curved. So we're going to go to the enclosure in the structure list. I'm going to activate that component, which means we're ready to select components from that body. We're ready to select faces from that component. And we're going to select those faces there, which are the curved faces. All right, let's go there. There. Oh, press Control to select multiple faces. And you might be saying, well, the nose cone's curved. Why don't you select that as well? I'm going to keep that as a separate selection because I want to apply an even finer mesh and other conditions to the nose cone. So we'll keep it separate for now. All right. I'm just going to call this body. Or maybe I'll just call it rocket body. Because it's all the faces excluding the fins and the nose cone. All right. You want to make another one for the nose. Just rename that to just body. All right, select just the nose, create a name selection for that, call it nose. That'll allow us to later on just select the nose and make some specific instructions for meshing. Then I'm going to make one for small faces. Remember I said you need curved surfaces and small faces. So let's go to the fin edges. And let's select just those really small faces. I'm going to hide this face for a second. So the reason we're selecting just the small faces by themselves is, again, the mesher needs specific instructions for these small faces to say, hey, I want you to make a really fine mesh near those faces. Otherwise, it just won't be able to capture what's happening around those small faces. And double check we've selected all the small faces around the fins. Very good. Name selection, fin edges. And then I believe the remaining rocket faces are just these two. Remember, we have to make a name selection for every face. Fins. So every surface on that rocket has been selected just once. Now we need to do the boundary condition surfaces, which is the enclosure. Symmetry planes, that's going to be this surface and this surface. Because we're slicing our problem into 4, we're later going to say that we want it to be symmetrical about that point and that plane and that plane. So it creates a full 360 degrees. So what we're going to do is group those together and call them symmetry. And then we're going to show some more faces by doing right-click Show All, because I need to select some other faces on this enclosure. We need to do the inlet. That's going to have its own boundary conditions. I'm just going to call that inlet. And then we'll do the same for the outlet. Okay, and the only remaining faces now are these two. We're just going to call that wall. Because what we're going to do is we're going to treat this face and this face as a wall surrounding our rocket. Inlet, outlet, and the walls. And now every face has been selected once. It's a bit of a tedious process, but it's going to give us heaps of control down the line. And we're done with SpaceClaim. Hallelujah. Now we can go to rocket enclosure .scdoc. And this is what we're going to be able to then import into the CFD software. So we've done a lot. Let's just very briefly go over what we've done. We created a little rocket model and we simplified it by slicing it into 4. We double checked that it was airtight and it didn't have any missing faces or anything. We created this sort of bubble of air around it. And then we created bodies of influence, far and near. And then we created name selections, which will make sense later on. So we're ready to go to Fluent. So the next step is to open up Fluent. And there's a couple of different ways of doing this. If you have the 2020 version of the student Ansys, you can just go to this 2020 folder here, and there will be a button that looks like this blue button here. It'll be Fluent 2020. Or you could just type in Fluent and it should come up. Now, if you're using the 2021 version, I found that there are a couple of issues where it didn't come up in this list, but rest assured, Fluent is on the system. You just have to do it in a bit more of a roundabout way. So for those of you using 2021, I'll just show you how to do that. I'm just going to save this and close SpaceClaim. You want to open something called Workbench 2021. And Workbench is like, if this software is like a tree, you've got the very top, you've got this Workbench, and then it branches down to Fluent, SpaceClaim, and it goes downwards. Workbench is the very top of the hierarchy of this software. So it allows you to view your entire project in one window, and you can take some SpaceClaim data and then pump it into Fluent, and then take the Fluent data and pipe that into something else. And you can create this flow chart, which I'll show you now. Let's see if I can maximize this screen. Okay, so we're going to go to, in Workbench, we're going to go to Fluid Flow, Fluent with Fluent Meshing. It's very important that you choose the with meshing one. And we're just going to drag that system into here. And for example, you could have, I don't know, maybe you wanted to have a static structural analysis with the pressure forces acting on whatever shape you're analyzing. You could then take the results and sort of drag and drop them into this static structural analysis. We're not going to be doing that today, of course, but it's just an example of how you can build up a project in Workbench. This is the roundabout way of doing it for the 2021 people who can't just type in Fluent. You have to open Workbench, and then with your geometry, you're going to say import geometry and go to rocketenclosure.scdoc. And just select update by right-clicking on geometry, go to update. And then mesh, you can right-click and go edit. And this will open the Fluent launcher. I'm not sure why you have to do it this way in the 2021 version, but this is the only way I could figure it out. And this is the launcher window for Fluent. You can't just straight away open Fluent. You got to double check a couple of settings. So you want to double check that you're using the right number of processors, as in how many cores does your processor have on your computer? And mine happens to have 6. I know that by going to, you go to this PC, right click, properties, and it will tell you your processor. My processor is an Intel i7. And then I can look that up in Google and it tells me I have 6 cores. So the option here, number 6, is saying how many cores do I want to devote to meshing? How many cores do I want to devote to solving? It's important to note that it doesn't include virtual cores. So my CPU has 6 physical cores and 6 virtual cores, meaning they might advertise it as 12 cores, but it needs to be just the physical cores. You can't include the virtual cores. Also, if you have a GPU, I can put that up to 1 if you have a dedicated GPU. If you don't have an actual GPU, then you just keep that at 0. Working directory, you can always mess around with that. Fluent root path, you probably don't need to mess with that, and that's probably good to go. So then you'll press start. It might take a little while in the 2021 edition. But this is the Fluent Mesher screen. So this is where we're going to build our mesh. And then we're going to take it to the final screen, which is the Fluent Solver screen. And what we're going to be doing is following this workflow on the left-hand side. This is called the watertight geometry workflow. It should automatically be selected for you. If not, you can go to this drop-down menu and select watertight geometry. First thing you do is import your geometry by clicking import geometry, and you just work your way down. So we'll click on the 3 dots here to choose which file we want. I'll go to downloads, Rocket Enclosure. And as soon as I select that, it's going to automatically start importing. And it will take a little while to import, especially if you're on an older computer. So we're around about an hour now. And what I'm going to do is I'm going to finish up there, and we'll show you how to build the actual mesh in Fluent and how to solve in Fluent next time. So we're going to have a double workshop. So today's workshop was all covering SpaceClaim, and we learned how to prepare everything for Fluent. And the next workshop is going to be the really fun one. And I'm hoping we can do that over Zoom and everyone can be there, and I can show you how we make a mesh, how we refine that mesh, make it a really high quality mesh, and then actually pump that through the solver and then get some really cool visualizations and solve for different velocities and pressures and forces. So thanks so much for watching, and we'll see you next week with part 2 of Ansys CFD. Bye. Hey everyone, just a little bit extra that I thought I'd chuck on the end of this video. I mentioned that I'd talk about Leap Australia's tutorials, and they were so helpful with teaching me this stuff. I thought I'd show you. If you just Google Leap Australia, the first link is their website. And if you scroll down on the right, there's the Leap Learning Hub. If you click on there, I've already been logged in, but just create an account, log in, and what will happen is you'll have structural, fluids, and electronics tutorials. And they have a huge range of tutorials from SpaceClaim and Ansys meshing and FEA tutorials that you might want to perform. They also have fluids tutorials. For example, if you say getting started with fluids, they'll show you how to build geometry in SpaceClaim and how to mesh it properly, and they'll give you heaps of examples. So that's going to be really helpful for a lot of you. And you can see they've got tons of stuff. So after this workshop, it's not the end of your learning journey. There's plenty to check out on Leap Learning Hub. All right, we'll see you in 2 weeks' time for part 2. Cheers, bye.